Good morning, class. We are looking at section 1, angles and their measures. This would be chapter 5 of the text, trigonometric functions, 5.1, angles and their measures. And the objectives are convert between decimal and degree, minutes, seconds, and so on. Find the length of an arc, convert from degrees to radians, area of a sector, and linear speed of an object. So first, I'm going to leave you to look at those later on your own. I'm hoping everybody remembers logarithmic properties. These are logarithmic properties. Here's the definition. When you go from the exponential format to the logarithmic format, and here's the basic properties. Log 1 with any base is 0. Log b base b is 1. So on and so forth. These are all properties that you should be very comfortable with. You've visited a number of times in algebra. And logarithmic functions and exponential functions are inverse functions, class. Inverse functions. And because they are inverse, they are symmetric with respect to this line, y equals x. This is just to refresh your memory about what has been before you. Now, we are going to look at some definitions such as vertex, line, ray, initial side, terminal side, positive angle, CCW, counter clockwise, negative angles, CW, counterwise. My apologies, clockwise. Standard position, okay? So a ray in essence, okay, this is a line and ray is a half line where it stops at some point. Where it stops, it is its vertex. This is the initial side. This is the vertex. And this is the terminal side of an angle. And this angle, which in this case we're going to call it alpha, is counterclockwise. And therefore it's a positive angle. If you look at its clockwise rotation, it's a negative angle. Just for the sake of argument, if this is, let's say, 60 degrees, the whole thing is 360, so this is minus 300 degrees. Now, here's your initial side. Here's your positive angle that goes more than one revolution. More than one revolution, and we still have the vertex here. Counterclockwise rotation, positive angle. Now, what is standard position, everybody? If you look at the grid that we have, we put the initial side of the angle along the positive side of the x-axis, the terminal side wherever it might be. Now we say the angle it's in standard position. Standard position meaning the initial side is along the x-axis. And of course, CCW, counterclockwise, this is positive. Again, we have a standard position, but this one, theta has a negative value. So, vertex, line, ray, initial side, terminal side, positive angle counterclockwise, negative angle clockwise, and what do we mean by standard position? Initial side on the x-axis. Let's look at quadrants, quadrantal angles, right angle, straight angle. So let's look at some of those. So if you again look at the grid, here's the 0 degrees, 90 degrees, 180, 207. This is called quadrant 1 between 0 and 90 degrees, quadrant 2 between 90 and 180 degrees, just the way we learned about the rectangular coordinate system, quadrant 3 between 180 and 270 degrees, and quadrant 4 between 270 and 360 degrees. So what are quadrantal angles? Quadrantal angles have a terminal side that lies on the x-axis at 0 or 180 degrees, or the y-axis at 90 or 270 degrees. So take a look at the concept here. These are all examples of quadrantal angles. Starting with this, again, this would be 0 degrees, okay? If the terminal side is on that, the assumption is all of them, the initial side is here. If the terminal side is on 0, 0 degrees. If the terminal side is on the y positive side, it's 90 degrees. If it's on the x negative side, is 180 degrees. If it's on the y negative side, is 270 degrees. And if it goes a complete revolution, comes back to 0, is 360 degrees. All of these are quadrantal angles. Now, 180 degrees is also called the straight angle. So let's continue with the thoughts. In this case, clearly theta lies in the second quadrant, right? Between 90 and 180 degrees. What about here? In the fourth quadrant, it's between 270 degrees and 360 degrees. This is a quadrantal angle of 270 degrees. So again, remember 90, 180, 207. And if you go back to 0, 0 or 360 degrees. Well, terminal side and the initial side, if you have a complete revolution, one revolution, 360 degrees, 360 degrees. Here's the vertex, here's the initial side, and this along the positive side of the y-axis is the terminal side, giving us 90 degrees, right angle. 1/4 of a revolution, CCW counterclockwise or 90 degrees. And this one is a straight angle, 180 degrees. So the initial side, obviously along the positive side of the x-axis, and the terminal side along the negative side of the x-axis. Straight angle, half of revolution counterclockwise, 180 degrees. 180 degrees, everybody. Most of these definitions should be coming back to you. You should have had them in basic algebra, trigonometry, or geometry courses that you've seen before. All right, we want to draw the angle, and remember, we basically start with just to give you an idea. You start with this. the positive side of the x-axis as your initial side. We want to go 45 degrees. We go this way 45 degrees, which is, remember, this is 90 degrees, so we go half of that in essence. 45 degrees. 90 degrees goes on the positive side. Negative goes on the negative side. So clockwise. So this is 90 degrees. This is negative 90 degrees. Or you can think of it as 270 degrees. Again, everything is given to you. We are going over the solution. You have all of these questions, definitions. We want to go with 225 degrees. Notice that 225 is larger than 180. So going back to this is your initial side. So if you go all the way to here is 180. So you go further by 45 degrees, and that becomes 225 degrees. So the initial side along the positive side of the x-axis, 225 degrees. Again, this way is 180 degrees, so you go another 45 degrees. Notice 405 is more than 360 degrees. A complete revolution is 360 degrees. Since this is more, so you go a complete revolution, and what else? If you subtract 360 from 405, you go 45 degrees. So a complete revolution and more by 45 degrees by this much again. Again, remember this, maybe I write it. This is 360 plus 45 degrees. So in essence, 45 degrees and 405 are the same. They have the same terminal side. That's the meaning of it. All right, so that's drawing angles. Now we want to convert between decimal and degree, minute, second measures of angles. Counterclockwise, CCW, revolution. A complete revolution is 360 degrees. 1 degree is 60 minutes. We have a prime here. 1 minute is 60 seconds, double prime. In other words, you could say this is 60 times 60, 3,600 seconds. Now we want to convert 40 degrees, 12 minutes, 5 seconds to decimal in degree. That means 40 point something. That's the meaning of it. How do we do that? Well, again, remember that 1 degree is 60 minutes, which means 1 minute is 1/60th of the degree, and 1 second is 1/3600, 1/60 times 1/60th of the degree. So we should recognize that. So again, from here, everybody from here, we can go to here. Understand that, right? That's the same meaning. If 1 degree is 60 minutes, 1 minute is 1/60 of degree, 1/60th of the degree. If 1 degree is 3,600 seconds, then 1 second is 1/3600. So 1/3600th of degree. So let's do it as follows. So we're going to write 40 degrees plus 12 minutes plus 5 seconds. And the 12 times 1 over 60. The 5 times 1 over 3600. You can write 1 over 60 times 1 over 60 or what I have here. So let me write that for you here. So you could just write here, right? 1 over 3600. Now, this is in degrees, this is in degrees. So this one is 12 over 60 or 1/5 or 0.2. This is very straightforward. This is 5 over 60. That means 1 over 12 times 1 over 60. And we end up with 0.0014. Now, if you add all of those are in decimals. We end up with 40.2014 degrees. So let's quickly recap. We want to convert this 40 degrees, 12 minutes, 5 seconds, into decimals. So 12 minutes times 1 over 60 becomes in degrees. 5 times 1 over 30, 600. This is 1 over 30, 600. And just add them. What if we want to go back? What if we have a decimal notation of 78.562 degrees and we want to go to DMS, degrees, minutes, seconds format? And of course, we are going to round it to the nearest second. So let's see how we do that. First of all, this is 78 degrees, very straightforward. This is 0.562. And if you go back again here, 1 degree is 60 minutes. So we can multiply this by 60 and make it into minutes. So this part, fractional part, the decimal part, if we multiply it by 60, this is now in minutes. Okay, so we have 78 degrees, 33.72 minutes, but we don't want to write it as 33.72 minutes. We want to write it as minutes and seconds. So we keep the 33, but 0.72 minutes. 1 minute is 60 seconds. So 0.72, if I multiply it by 60, so first let me write it. So this is fine. We have the degrees, we have the minutes, but this one, we want it as a whole number. So if I multiply this one by 60, this changes to seconds. So this one is in degrees, we keep it. This one is in minutes, we keep it. This one, which is in minutes, we multiply by 60 to change it to seconds. The reason we do that, because it's less than 1. We get the following. And round to the nearest second. So this is fine, this is fine. This one, we have to round it to a whole number, which becomes 43, which means 78.562 degrees is the same as 78 degrees, 33 minutes, 43 seconds. A quick recap. A complete revolution is 360 degrees. 1 degree, we cut it into 60 equal pieces, we call it minutes. 1 minute, we cut it into 60 equal pieces, we call it seconds. So degrees, minutes, seconds. And the conversion is that if 1 degree is 60 minutes, then 1 minute is 1 over 60th of a degree. If 1 minute is 60 seconds, then 1 second is 1 over 60 times 1 over 60. That means 1 over 3600 of a degree. That's how small it is. Radian. Radian has a definition. Here's the definition. The measure of a central angle subtending an arc equal in length to the radius. And it works out to be almost 60 degrees, 57.3 degrees, or 180 divided by pi. And remember, pi, everybody, is not 3.14, it's 3.14159. Let me write that. Continues indefinitely. So that's an irrational number. So pi equals 3.14159, and it continues indefinitely. So when we say 3.14, it's an approximation. You want to pay attention to that. Now, when we look at this, the idea is that if you have a circle such as this one, and this arc has a length equal to its radius, then the measurement for this angle is 1 radian. Same thing works out here. It doesn't matter how big or small the circle may be, the length of the arc, in this case is 3, must be the same as the length of its radius. If it's 1, it's 1. If it's 3, it's 3. If it's r, in general, r. So the length, the arc length must be equal to the radius. Now, let's find the formula for the arc length of a circle. Let's find a way to calculate this. Well, arc length is the length of the arc of a portion of a circle, part of a total circumference of a circle, given a central angle theta, S equals R times theta. And here's the reason. First, if you were to compare these two, the ratio of theta to theta 1 is the same as S to S sub 1. And everybody remembers the circumference is 2 pi r. The circumference of a circle, 2 pi r, where 2 pi represents a central angle, a complete revolution. So if we replace the 2 pi with the angle theta, that means S is r theta. In essence, this is the proof that the arc length is calculated using r theta. S equals r theta. Needless to say, theta must be in radians. Theta must be in radians. S equals r theta. And so with that being the case, we want to find the length of an arc of a circle of radius r. So r is given as 4 meters subtended by a central angle of 0.5 radians. So theta is given as 0.5 radians. So basically S equals r theta. S equals r times theta. And it's important when you do word problems, you want to write the given. So in this case, it's pretty obvious. So if you didn't, that would be fine. But so this is r. And this is theta. And 4 times 0.5 is 2. As far as the units, you always use the units of the radius. It happened to be in meters. Proper units are extremely important. All right, how do we go from one format to the next? In other words, radians to degrees and vice versa. Remember, a complete revolution is 2 pi radians or 360 degrees. So half of that, it's 180 degrees or pi radians. Okay, so that's a simple definition. One complete revolution, 360 degrees or 2 pi radians. Half of that is 180 degrees pi radians. So pi radians and 180 degrees are the same. Therefore, what is 1 degree? Pi divided by 180 radians. What is 1 radian? 180 divided by pi degrees. I like to use this formula, which is the synopsis of everything that is mentioned here. D over 180 is R over pi, meaning one of those two are missing. If the degrees are given, put it up here and find the R. If the radians are given, put it here and find the D. So some of the common ones, and again, some of you may remember 0 is 0, but for example, 30 degrees is pi over 6. Because 30 is 180 divided by 6. 45, pi over 4. 60, pi over 3. 90, pi over 2. 120, 2 pi over 3. 135, 3 pi over 4. 150, 5 pi over 6. 180 pi. And there are more. You don't have to memorize them. I hope you remember them because these are common. At the very least, some of the very basic ones, for example, the quadrantal angles, obviously, 30, 45, and 60 are important angles we should remember. Okay. All right. We want to convert from one format to the next. In this case, degrees to radians. We can use that. And if we have the degrees, that means over here we have the number and the R is missing. Or for example, in this case, we can say 30 times pi radians over 180 degrees. So there are different ways of doing it. You can use this format. You can use this one or this one. In this case, we're going to use pi times 1 over 80. And sometimes it becomes a nice and easy number such as pi over 6. Sometimes it's not. These are mostly common arcs. You may remember this was 2 pi over 3. So if you multiply it by pi over 180, or as I mentioned, let me just write this here in case if you want to go in this case, let's put 180 here, a pi here. So if you want 120 degrees, so you put 120 degrees, and then you find the R. And I hope you see that the cross product will give you this. Okay? Cross product will give you that. For this one, again, go with the same thing. You can replace the 120 with minus 60. Cross product will do that, or just multiply this by pi over 180. So this becomes 2 pi over 3. This becomes obviously, remember, 60 degrees is pi over 3. So this is negative pi over 3. Now, 104 is not one of those common arcs, again. So you can replace this one with 104 or just multiply this one by pi over 180. And it becomes something different than the others, 1.815 radians. And look at this one. It's almost equal to that because that's the nature. When it's not one of those common arcs, it becomes an approximation. All right. If we want to go back, if we want to go from radians to degrees, then again, you can put it in this one. For example, here, put the negative pi over 2 over, instead of R and do the cross product. Or simply put multiply by 180 over pi. So again, two ways. In this formula, replace whatever is given, radians is given, so minus pi over 2, and the cross product will do that, or multiply this by 1 over 80 times pi. Obviously, the two cancel each other. You get negative 90 degrees. I think most of you know that pi over 2 is 90 degrees, so negative pi over 2 is negative 90 degrees. This one, some of you may know pi over 6, we've mentioned that pi over 6 is 30 degrees. In fact, you remember that. So it's 5 times that. 5 times that is 150 degrees. Or simply put, multiply this one by this. So again, I'm showing you, you can go with that route for this one, either that one or that, two different ways, either way is fine. And in this case, the pi's cancel each other, and 180 divided by 6 is 30 times 5, which is 150. However you come up with the answer is fine. And now 5 radians times 180 over pi, or replace this one with 5 and do the cross product. And this gives you 286.48 degrees. So conversion between degrees and radians is very straightforward. Could somebody read this question, please? Anybody feels like reading it for us, please?
The latitude of the location L is the angle formed by a ray drawn from the center of Earth to the equator, and a ray drawn from the center of Earth to L. Glasgow, Montana is due north of Albuquerque, New Mexico. Find the distance between Glasgow, approximately 4.15 or 4.49 north latitude, and Albuquerque, approximately 35.03 or 35.5 north latitude. Assume the Earth's radius is 3,960 miles.
Excellent. Thank you so much. So the information is given, and we just need to write the given. So what do we have here? Here's the equator. Albuquerque has this central angle. Glasgow has a different angle. So let's write them. The central angle between the two cities would be the difference between the two. So this one, the larger one, is 48.15 degrees, and the smaller one is 35.08 degrees. So the central angle between the two cities is the difference between the two numbers. We have that. Now we want to go with S equals R theta, because this is the arc length we are looking to find. This is the distance between the two, the arc length we are looking for. Therefore, we want S equals R theta, which means we're going to change this to a radian. In other words, times pi over 180, and then times the radius of the Earth, which is given. So first we change this to a radian by multiplication by pi over 180. S equals R theta. This is R. Let me. And their product, this number times this, and the units, whatever units of the R. Their product is about 903 miles. That's how we approximate the distance between the two cities based on the latitude of their locations. Find the area of a sector of a circle formed by a central angle theta. And the formula is half of R squared theta. Again, comparing and understanding. The concept is you have a wedge, if you will, this portion. We want the area of this portion known as a sector. Known as a sector. The ratio of theta to theta 1 is a over a sub 1. We know the area of a circle is pi r squared. Remember, pi doesn't represent the theta, actually represents half of it. So pi, this is half of 2 pi, and replace the 2 pi with theta. And that's the justification as to how we arrive at the area of a sector. Area equals 1/2 r squared theta. So this is the proof using the area of a circle pi r squared, replacing the pi with half of 2 pi, and now 2 pi with theta. So this thing, in essence, represents the theta, and that's how we arrive at this, which now gives us this simple equation. Find the area of a sector of a circle of radius 5, so r is given, formed by an angle of 60 degrees. So simply put half of r squared theta. Theta must be in radians. By now, everybody knows 60 degrees is pi over 3. So you don't have to worry about that. So I'm assuming a common arc such as 60 degrees, everybody knows is pi over 3. So half of r 5 squared times theta pi over 3. It is extremely important to pay attention to this. This must be in radians or the answers are wrong. So this is 25. This is 6. 25 pi over 6 precisely. This is the exact answer, everybody. If the question is give us the exact answer, you're done here. But it's asking for 2 decimals. So you write at least 3 decimals to make a decision, okay? Write down 3 decimals and make a decision. And what are the units? The units of the radius. Find the area of a sector of a circle of radius 2 feet formed by an angle of 30 degrees. Again, we need to have this in radians. It's one of those common arcs everybody knows is pi over 6. Everybody, this is pi over 6. We should know that. Half of r squared, half of 2 squared times pi over 6. Now, 4 divided by 2 is 2 divided by 2. So this is pi over 3. Precisely pi over 3. Exact answer, pi over 3. And with a couple of decimals, 1.05. And the units are units for the radius. Units for the radius.
I want to ask,
Go ahead.
for the area, should it be square feet or just feet?
Square feet. Yes, I'm glad you mentioned that. You are absolutely right. Square feet. Thanks. Absolutely. It's square feet. You're 100% correct. Thank you. All right. Yes, definitely square feet. All right. Find the linear speed. Find the linear speed of an object traveling in circular motion. Suppose that an object moves on a circle of radius r at a constant speed. If s is the distance traveled in time t on the circle, the linear speed v of the object is defined by total distance over total time. Total distance over total time, and distance is s over t because it covers the arc length of s. It's a definition of a linear speed. The angular speed, which is represented with omega, the Greek lowercase letter omega of this object, is the angle theta, the angle measured in radians, swept out, divided by elapsed time t. which means omega is the total amount of angle over the total amount of time. So theta over t. Let's do some manipulation. V is S over t, and we know S to be r theta. V is S over t. S is r theta. Let's separate this into r times theta over t. The reason we do that, because we know theta over t is omega, so V is r times theta over t. And theta over t is defined as omega. V is r omega. V is r omega. The linear velocity is r times the angular velocity. Could somebody read this question, please?
A child spinning a rock at the end of a 3-foot rope at the rate of 160 revolutions per minute, RPM. Find the linear speed of the rock when it's released in miles per hour.
Perfect. Thanks. Now, first of all, revolutions is a complete revolution per minute. We put RPM. If it's per second, we may write RPS for short. So I just want to remind everybody. And then, of course, what I've added here, again, the V is S over T or R omega. We have it from the previous page. I want you to pay attention to this. Omega is defined as theta over T, or 2 pi times RPM, revolutions per minute, okay? And so what is given when we read this question? The radius is given, 3 feet, and omega is given as RPM, 160. So we write the given R, 3 feet, omega 160 revolutions per minute, RPM. We are interested in finding V. So first and foremost, we are going to change the format for omega. It has a different units. The units are revolutions per minute. Each revolution is 360 degrees, or better yet, 2 pi radians. So one revolution is 2 pi radians. So this has to get multiplied by 2 pi. So I hope you see why we multiplied by 2 pi. When we multiply by 2 pi, then RPM, revolution per minute, will change to radians per minute. So again, when we multiply by 2 pi, the revolution changes to radians. Per unit of time doesn't change. It's per minute, per second, whatever it might be. And so in this case, we multiply 2 pi by 160, we get 320 pi radians per minute. And it's a good practice to keep it as pi at the end. If you have to change it accordingly, you will do that. But pi is an exact answer. And V is R omega, R omega in radians per minute. So 3 times 320 pi, it's precisely 960 pi, and roughly 3016. Now, the units are feet per minute. Why is it feet per minute? Well, this was RPM, revolution per minute. That's why the minute. And the radius was 3 feet. Now, we want to go with miles per hour. So we're going to remind everybody that 1 mile is 5,280 feet. So we're going to change that accordingly. 1 hour is 60 minutes. 1 minute is 60 seconds, and so forth, if we have to make the adjustment. So for now, 316 roughly feet per minute. We want to go to miles per hour accordingly. So we want the miles at top. So 1 mile is 5280 feet, right? So we can say 1 over 5280 or 5280 over 1. Because we want the miles at top, we put 1 mile over 5,280 feet. Okay. Okay, so that takes care of that. Minutes, we want to go to hours. So we're going to put 1 hour is 60 minutes. And we can put, remember, you can put 1 hour at top, 60 minutes at the bottom, or vice versa. It's a unity. It makes no difference. However, since we want the hour at the bottom, so if we put the hour at the bottom, 1 hour at the bottom, then 60 minutes goes at top. And so now, as you can see, this minute cancels out this minute, this feet cancels the feet. So 316 times 1 times 60 goes to the top, over 5,280 times 1 goes to the bottom, and it simplifies to roughly 34.3 miles per hour. I went over this with details, so I hope you remember the conversion from basic algebra that you have learned, so you can easily do the conversions. An object is traveling around the circle with a radius of 8 inches. If in 40 seconds a central angle of 1/3 radian is swept out, what are the linear and angular speed of the object? Anytime you have a word problem, you want to write the given. So you are going to start rereading the question and say, okay, R is given as 8 inches. In 40 seconds, t is 40 seconds, the central angle theta is 1/3 of a radian, and we want V and omega. So R is 8 inches. Over the course of 40 seconds, we cover 1/3 of a radian, and we want both V as well as omega, and omega is defined as theta over t. Theta over t. 1/3 over 40 makes it 1 over 20. 1 over 20, roughly 0.008 radians per second. Radians per second. And V is R omega. R omega. R is 8. Omega, let's use this one because it's exact. And 120 is divisible by 8, becomes 1 over 15. Again, this is exact. And then with a bunch of decimals, normally they ask you how many decimals. If they don't, you want to go with many, many, many decimals to be on the safe side. And it's inches per second. So the linear velocity is 0.067 inches per second. The minute hand of a clock is 6 inches long. How far does its tip move in 15 minutes? How about 25 minutes? And they want us to go with a couple of decimals. And so let's write the given as we read this question. We are taking the radius to be 6 inches. In part A, 15 minutes, over the course of 15 minutes, we want to find the theta, and therefore S, because it says how far does its tip move. So it's asking for the arc length. And some of you may just look at it and say, okay, this is pi over 2, and that's fine. Or you might say 15 minutes. If you divide it by 60, that gives you 1/4 of a complete revolution. So 1/4 times 2 pi is pi over 2. So whether you see the 15 minutes, I guess most everybody knows 15 minutes, like 30 minutes is half of the revolution. So it's or pi in this case is pi over 2, and s equals r theta. R was 6, so times pi over 2, and it's precisely 3 pi. This is the exact answer. We go with a couple of decimals, and we use the units here, okay? The units of the R radius. In the second part, 25, we just divide the 25 by 60, and that's the number of revolutions, and we multiply it by 2 pi. The reason I did this, so it becomes clear how we arrive at 25. 15 is straightforward, I think everybody knows. But 25 may not be. So 25 divided by 60 is the number of complete revolutions. Times 2 pi is 5 pi over 6. And so in this formula, you replace the pi over 2 with 5 pi over 6. And that gives you precisely 5 pi and approximation 15.71. Again, units of the radius, 15.71 inches. All right, class, we're going to move on. A 40-inch pendulum swings 20 degrees each second. How far does it tip, move each second? And again, we want to go with 2 decimals. We want to write the given. So it's 40-inch long, so that would be the radius. And theta is 20 degrees. We want to see how far it moves. So we are looking for S, the arc length. So we have to change this to radians. Remember, this has to be in radians. 20 degrees. Remember, 180 degrees is pi, so 20 degrees is pi over 9, or just go over the process and do the, conversion from degrees to radians. S equals R theta, R theta. 40 pi over 9 is an exact answer, everybody. 40 pi, because the product. 40 pi over 9. And then we go with however many decimals they ask. Again, bear in mind, you have to go to the 3rd decimal to make a decision, okay? So make sure you have many decimals, then you make a decision. And the units are the units of R, the units of the radius, therefore inches. A water sprinkler is to cover a field of 100 square yards in the shape of a sector of a circle of radius 5 yards. What is the angle needed for this rotation? Well, let's write the given. The area of a sector, which is half of r squared theta, is given as 100 yards squared. Radius is 5 yards. The angle theta is missing. Now, let me just quickly change this to 5, okay? It's 5 yards. And so A is 1/2 r squared theta. So replace the A with 100, R with 5. Actually, let me do this, everybody. This is, let's change this to 15, and this is 15. And let's erase this. Now it actually works out. So that must have been, this must have been a typo. Okay. Let's plug in everything. And what is missing? Theta. So everything, this is 100, this is 1/2, R is 15 squared, and theta is missing 15. When you square it, you get 225. When you divide it by 2, you get 112.5. So let me actually quickly do that. This is 225. This is 112.5. So theta is 100 divided by 112.5, which gives us 8/9 radians. We change it to degrees, and one way is d/180 is r/pi. What is the angle needed? Normally they want it in degrees, class. Of course, it's not mentioned here, so if you didn't put it, would be okay, but normally they are asking for degrees. In this case, you replace the r with 8/9, and the cross product 180 times 8/9 divided by pi is the degrees, and you go with 2 decimals. Again, as usual, class, you want to go with more decimals to make a decision properly. Okay. A windshield wiper's arm and its blade are 30 inches long. If the blade is 24 inches, the blade is 24. And the wiper sweeps about the angle of 125 degrees. So the angle is 125 degrees. How much window area can it clean? Well, I want to make sure everybody understands. We have to go with the area of a sector and the concept. Okay. This total area can be calculated, and this is the area that is being cleaned. This is the area that is not being cleaned, okay? Because it's the wiper, okay, arm and its blade. This is the arm, this is the blade is the portion that does the cleaning, not the arm. So you calculate the whole thing, and then you calculate this little gray area, and their difference is the concept here. So R1 is 30 inches, meaning the whole thing, arm and the blade is 30 inches. That's the R. The blade is 24, everybody. This is 24. This is 24. And this part is 30 minus 24, or in this case, 6 inches. Theta is 125 degrees. So we calculate the total area. That means we calculate the blue one and the gray one using R equals 30. Then we calculate the gray one using the difference between 30 and 24, which is 6. And their difference is what we are looking for. I hope everybody understands. I'm going to quickly recap. The whole area uses R equals 30. And then the gray area uses R 30 minus 24, which is 6, this red one. We calculate both sectors. The difference is the answer. So half of R1 squared theta minus half of R2 squared theta. And R1 is 30, R2 is 30 minus 24 is 6. Theta is 125 degrees, and it's 25 pi over 36. I'm going to assume the conversion is not a big deal to anybody. And so half of 30 squared times 25 pi over 36. We are looking at this formula, minus half of 6 squared times 25 pi over 36. So at this point, you plug it into a calculator and you come up with the answer, everybody. So this one, 11,250 pi over 36, and this one is 450 pi over 36. The difference is 300 pi, and we change the pi to a decimal representation with 2 decimals, and the units of the R squared, because it's the area. The units of the R squared, because it's the area. An object is traveling around a circle of radius 2 meters. It travels 5 meters in 20 seconds. What are the angular and linear speed? Again, we've done many of this by now. You should be pretty comfortable with that. Let's write the given. Radius is 2 meters. S is 5 meters. T is 20 seconds. V and omega are of questions. So V is S over T. We have the S, we have the T, and it's 1/4 of a meters per second. We also know that V is R omega, so omega is V over R. V is R omega, omega is V over R. 1/4 over 2 makes it 1 over 8 radians per second. A centrifugal force ride, similar to gravitron and amusement ride, spins at 22 revolutions per minute. If the diameter of the ride is 12 meters, what is the linear speed of the passenger in kilometers per hour? Well, again, let's write the given. 22 revolutions per minute, 22. Omega is 22 RPM. Radius, the diameter is 12, so the radius is half of that, class. This is 12 meters, so R is half of that. And we are interested in finding V. First, let's find omega, which is 2 pi times this, because this is RPM. We want to make it radians per minute. So 2 pi times RPM, 2 pi times 22. That is omega. And the velocity is R omega. 6 times 44. And that gives us 264 pi meters per minute. Now we want to go to kilometers per hour. So we do the conversion again. Remember, 1 kilometer is 1,000 meters. 1 hour is 60 minutes, and so forth. So we want kilometers per hour. So we have this one meters per minute. So 1 kilometer is 1,000 meters. 60 minutes is 1 hour. You put them in a right spot. Remember, because you want kilometer at top, hours at the bottom. Okay. And so this number times this number times this number divided by 1,000, and that gives us 49.763 kilometers per hour. And again, however many decimals. A DVD drive has a maximum speed of 7,200 RPM. If a DVD has a diameter of 12 centimeters, what is the linear speed in kilometers per hour of a point 5 centimeters from the disk center if it is spinning at a rate of 5,400 RPM? Well, first of all, we are concerned with this point. So the R at a point of 5 centimeters matters, okay? This is the maximum speed, but we are talking about this, okay? 7200 is the maximum, so we want this one. This is the omega, this is the R, and V is missing. So again, this is the maximum speed. Don't mix them up with what is given. So omega is in RPM. We are going to multiply it by 2 pi and making it into radians per minute. V is R omega. So you multiply this number by R, 54,000 pi, centimeters per minute. Remember, units of R per units of time. Now you want to change it, remember, to kilometers per hour. 1 kilometer is 1,000 meters. Remember, this is centimeters. 1 meter is 100 centimeters. So 1 kilometers per hour. So this one is centimeters per minute. So 1 meter is 100 centimeters. 1 kilometer is 1,000 meters. And 1 hour is 60 minutes. So this number times 60 over 100 times over 100,000. So 54,000 pi times 60 over 100,000. Those 3 zeros cancel that, 0 cancels that. And when you do the math, you end up with 101.8 kilometers per hour. Again, however many decimals that they ask you. The radius of each wheel of a car is 15 inches. If the wheels are turning at a rate of 3 RPS, revolutions per second, how fast is the car moving? And we want to go with mph, miles per hour. So the radius is 15 inches, and omega is 3 RPS, and V is missing. So the very first thing, we are going to multiply this one by 2 pi to make it into radians per second. V is R omega, 15 times 6 pi makes it 90 pi inches per second. And of course, that's an exact answer. We change the pi to 3.14159 and we use a calculator. We get this one. We are done. We want to change this to miles per hour. To do that, remember, 1 mile is 5,280 feet, and 1 hour is, since this is second, 3,600 seconds. So miles per hour. So inches per second. 1 foot over 12 inches, 1 mile over 5,280 feet, 3,600 seconds over 1 hour, and it will do the job, and you get 16.1 miles per hour.